Bipartite graphs. The most important special case of a k-colorable graph is when k equals to 2. This case is so omnipresent in combinatorics that it has its own name. Definition 11.4. A two-colorable graph is called a bipartite. Equivalently, G is bipartite if the vertex set of G can be split into the disjoint sets A and B, the color classes, so that each edge of G is adjacent to one vertex of A and one vertex of B. A generic example of a bipartite graph is shown in figure 11.2. Note that there are no edges within either color class. For example, all trees are bipartite as one can start at any given vertex, color it red, then color all its neighbors blue, then color all the second neighbors red, and so on. This coloring algorithm works as there is no cycle in the tree, so we will never get back to a vertex that has already been colored. Another example of a bipartite graph is, say, a square, hexagon, or octagon, where we can color vertices alternatingly. An easy example of a graph that is not bipartite is a triangle. Indeed, if a triangle has a red vertex A, then one of the two neighbors of A can be colored blue, but the third vertex of the triangle cannot be properly colored. It is also clear that no graph that contains a triangle can be bipartite, as not even that triangle could be two-colored, let alone the whole graph. Is it true that if a graph does not contain a triangle, then it is bipartite? As we can see in figure 11.1, this is not true as the pentagon provides a counterexample. There is nothing magic about the pentagon here. The reader can easily see that no cycle of odd length can be two-colored, and therefore no graph containing an odd cycle can be two-colored. The following theorem shows that with this we have completely characterized the bipartite graphs. Theorem 11.5. A graph G is bipartite if and only if it does not contain a cycle of an odd length. Proof. As we have mentioned, the only if part is easy. Suppose G contains the odd cycle A1, A2, A3 until A2m plus 1. Let us assume without loss of generality that A1 is red. Then A2 must be blue, therefore A3 must be red, A4 must be blue, and so on, and at the end A2m plus 1 must be red too. This is not allowed, however, as A1, A2m plus 1 is an edge. To prove the if part, let G be a graph with no odd cycles. Let V be a vertex of G and color V red. Define the color of any other vertex W as follows. If the shortest path from V to W has even length, then let W be red, and if the shortest path from V to W has odd length, then let W be blue. We show that this is a good coloring, that is, there are no two adjacent vertices that are the same color. Assume the contrary by first assuming that P and Q are two red vertices that are joined by an edge. Let the shortest path from V to P be P, little p, and let the shortest path from V to Q be Q, little q. Then little p and little q both have an even number of edges, so working from V through little p to P, then through PQ, then back from Q through little q to V, we get a closed walk C with an odd number of edges. Taking away edges that were used both by P and Q, this walk C splits into the union of edge disjoint cycles. As the total number of edges in these cycles is still odd, there has to be at least one cycle with an odd number of edges, which is a contradiction. If we assumed instead that both P and Q were blue, the same proof would work as the sum of two odd numbers is still even, so C would still have an odd number of edges. How many edges can a simple bipartite graph G on n vertices have? The author-reader should have an intuition at this point that the answer to this question will be some kind of an upper bound. Indeed, it is not difficult to create bipartite graphs with few edges. For example, forests have no cycles at all, so they cannot have odd cycles either. Thus, all forests are bipartite. We could think, however, that if we keep adding new edges without adding new vertices, then sooner or later an odd cycle will be formed. In fact, the complete graph Kn certainly has odd cycle if n is greater than or equals to 3. So where is the threshold? How many edges can we have in G without having an odd cycle? The forests only allowed us to go to n-1 edges. Will the final answer be some linear function of n, or maybe around n to the alpha, where 1 is less than or equals to alpha less than 2, or will it be just a constant factor below n choose 2, the number of edges in the complete graph? The following theorem shows that the answer to this question is closer to the maxima. Theorem 11.6. Let G be a simple bipartite graph on n vertices. Then G has at most n squared over 4 edges if n is even, and at most n squared minus 1, then divided by 4 edges if n is odd. Proof: choose G so that no other simple bipartite graph on n vertices has more edges than G. Denote by A and B the sizes of the two color classes of G. It is clear that each vertex of one color class is connected to each vertex of the other color class in G. Indeed, if there was a missing edge between the two color classes, we could add it to G, contradicting to our assumption. So G has AB, which is equals to A times n minus A edges, and the proof follows from elementary calculus. One simply has to find for which A in the closed interval between 1 and n is f of A, which is equals to A times n minus A minimal. The class of bipartite graphs we used in this proof, that is, bipartite graphs in which each vertex of one color class is connected to each vertex of the other color class, is an important one. Therefore, such graphs have a name. They will be called complete bipartite graphs. These graphs played a role in several exercises of earlier chapters. If a complete bipartite graph has color classes of size A and B, then we will denote that graph by KAB. So bipartite graphs can have a lot more edges than trees. We will see that accordingly they have a much richer structure too. To start, let us take a closer look at the consequences of theorem 11.6. Let H be a simple graph on two m vertices. If H has only m square edges, then H can be bipartite. Indeed, H can be KMM. If H has more than m square edges, then theorem 11.6 implies that H is not bipartite. In other words, H has an odd cycle. The following lemma shows that more is true. Lemma 11.7. Let H be a simple graph on two m vertices where m is greater than or equals to 2 and at least m squared plus 1 edges. Then H contains a triangle. Proof. We prove our statement by induction on m. If m is equal to 2, then H is a subgraph of K4, which with at least 5 edges. Theorem 11.6 shows that H is not bipartite, so it must have an odd cycle. This odd cycle must be a triangle as H has only 4 vertices. Now assume we know that the statement is true for all integers that are smaller than m and are at least 2. Let H be as in the statement of the theorem, and let f and g be two adjacent vertices in H. If the sum of the degrees of f and g is more than 2m, then they have a common neighbor t, and so FGT is a triangle. If, on the other hand, the sum of the degrees of f and g is at most 2m, then deleting f, g, and all the edges adjacent to them from H will decrease the number of edges in our graph by at most 2m minus 1. Note that the HFG is contained twice in the sum of the two degrees. Therefore, after the deletion of these vertices and edges, we are left with a graph of 2m minus 2 vertices, and at least m squared plus 1 minus 2m minus 1, which is equals to m squared minus 2m plus 2, which is equals to m minus 1 squared plus 1 edges. Such a graph contains a triangle by the induction hypothesis, so our claim is proved. Thus, we know that graph on 2m vertices with just one more edge than what is possible in bipartite graphs does not simply have an arc cycle, but also has a triangle, the shortest arc cycle possible. The real surprise, however, comes now. Theorem 11.8. Let H be a simple graph on 2m vertices m which is greater than or equals to 2 and at least m squared plus 1 edges. Then H contains at least m triangles. So if H has m squared edges, it may not have any arc cycles at all, but with only one more H must have at least m triangles. Note that there is nothing similar that would be true for trees on m vertices. A connected graph on m vertices and m minus 1 edges is a tree. Adding an extra edge, we get a cycle. In fact, exactly one cycle, but that cycle can be of many different lengths depending on the tree. Proof. Clearly, we can assume that H has exactly m squared plus 1 edges as additional edges will not destroy any triangles. We prove our statement by induction on m. If m is equal to 2, then our graph has 4 vertices and 5 edges, so it is K4 with an edge missing, and therefore does contain 2 triangles. Now assume the statement is true for all possible integers smaller than m, but at least 2. Let H be as in the statement of the theorem. Lemma 11.7 shows that H contains at least one triangle ABC. We have to find m minus 1 other triangles. We will distinguish 3 cases based on the number of edges connecting outside vertices to the vertices of the triangle ABC. We claim that if the number of all these edges is 2m minus 3 plus x for some x which is greater than or equals to 1, then there are x triangles formed by 2 vertices of the triangle ABC and a third vertex that comes from outside that triangle. Indeed, if such an outside vertex is connected to 2 vertices of ABC, then it forms a triangle with them. As there are 2m minus 3 outside vertices, our claim follows by Pigeonhole Principle. The outline of the proof will be thus. If there are many edges between ABC and the outside vertices, then there are many triangles spanned by 2 vertices of ABC and an outside vertex. If, on the other hand, there are only a few such edges, then there have to be so many edges among outside vertices that we can apply the induction hypothesis for their subgraph and an extra vertex. 1. If x which is greater than or equals to m minus 1, then we are done as we found our missing m minus 1 triangles. 2. If 1 is less than or equals to x which is less than m minus 1, then the total number of edges between A, B, C, and the outside vertices is at most 2n minus 3 plus n minus 2, which is equals to 3n minus 5. As ABC itself contains 3 edges, it follows that there are at least m squared plus 1 minus 3 minus 5, then minus 3, which is equals to m squared minus 3m plus 3, which is equals to n minus 1 times n minus 2 plus 1 edges within the subgraph R spanned by all 2m minus 3 outside vertices. If we omit the vertex of R, which has the smallest degree in R, it follows by the Pigeonhole Principle that we get a graph R prime on 2m minus 4 vertices that still has more than n minus 1 times n minus 2 times 2n minus 4 divided by 2n minus 3, which is equals to n minus 2 squared times 2n minus 2 divided by 2n minus 3, which is greater than n minus 2 squared. Edges. So R prime has strictly more than n minus 2 squared edges. That is, it has at least n minus 2 squared plus 1 of them. Therefore, by the induction hypothesis, there are at least n minus 2 triangles within R prime. As we said in the previous paragraph, there are X triangles spanned by 2 vertices of ABC and an outside vertex. In our case, X is greater than or equals to 1, so we have again found the n minus 1 needed triangles. 3. Finally, consider the case when the number of edges connecting outside vertices to ABC is not more than 2n minus 3. Note that we can assume that there is at least one such edge, otherwise R has m squared minus 2 edges. So adding any vertex of ABC to R creates a graph on 2m minus 2 vertices and m squared minus 2, which is greater than or equals to m minus 1 squared plus 1 vertices. And the proof follows by the induction hypothesis. That said, the number of edges within R is at least m squared plus 1 minus 2m minus 3, then minus 3, which is equals to m minus 1 squared. Adding a vertex of ABC that is adjacent to at least one outside vertex to R creates a graph with 2m minus 2 vertices and at least m minus 1 squared plus 1 vertices. And again, the induction hypothesis shows that such a graph must contain at least n minus 1 triangles. In other words, if we start with the empty graph on 2m vertices and keep adding edges to it at random, then as soon as we can be sure without looking that our graph has one triangle, we can also be sure that it has m triangles.